This is the single and double slit interference lab. So you should read through the lab, and page 3 you should have done from your observations, and same for page 4 and page 5. So page 6 you should read through. We have an equation here on page 7 which we are going to use when we do our graph, and this is for the double slit pattern. Okay, so on page 8 it says to use the data that you have in your table to create a graph of y versus m. That's with this equation here. So y is equal to m times capital D, which is the distance from the slits to the wall, which you should have measured, times lambda divided by little d. Okay, so now let's go to the table for the double slits. So this is on page 14. So you have the slit separation, which was supposed to be 0.25 millimeters, and the slit width, which was supposed to be 0.04 millimeters, and the distance from the screen, distance to screen, that should be distance to wall, so from the slits to the wall. And so, and then in your table here, you measured 2y, so divide what you measured by 2 to get y, and this is going on the x-axis, and y is going on the y-axis. So this is on the y-axis, m is on the x-axis, which means this is our slope when we do a linear fit. You want to use the slope to find the wavelength, and you have the slope is equal to capital D, which you measured, divided by little d, which you have recorded, and times the wavelength, which means the uncertainty for the slope, because the slope is proportional to the wavelength, is equal to capital D divided little d times this uncertainty for the wavelength. So plug in the slope that you have, find the uncertainty of the slope, plug that in there, solve for lambda, solve for the uncertainty for the wavelength, and tell me the wavelength plus or minus the uncertainty. This actually here is supposed to be for the red laser, but you can do the green laser here, and if you only did the green laser, then that's all you need. If you did the red laser, you can show the work for that later on. The wavelength for the green laser depends on which green laser you used, so hopefully you recorded that. It was either 532 nanometers for the green laser or 515 nanometers, and you should know which of those two you are looking for. Okay, so you got your wavelength with the uncertainty there. Okay, now you need to read through page 9. They're doing the theory for the single slit experiment on page 9. Read through this on your own. They're looking at 2 imaginary slits here, and they're saying that the light that's coming from this point here and the light that's coming from that point there are going to give you destructive interference, so they're going to cancel out. Okay, I think you should be able to answer this question on your own, why it doesn't work for an odd number of slits. If you want to try and figure out the answer to question 2 on your own, you can do that. Pause the video now because I'm going to give you the answer in just a moment. A lot of people struggle with this question, so I'm just going to tell you the answer. So why can't we not use a similar argument for constructive interference? So the argument was, take your slit, which goes from here to here, and divide it in 2, and look at the wave here and the wave here, and they're going to meet somewhere over here, way over here. and they're going to cancel out. That was the argument. But why can you not use this for constructive interference? So that means you would have the light here and the light here adding together to give you a bright spot. Well, it doesn't work because if you use the argument that they gave you before for destructive interference, after you already broke the slit into two separate pieces, then you'd have another piece, another point here, the light's coming over here, the light's coming here, and it could be that if these two are constructive, that this one and this one are destructive, and this one and this one are destructive. And if that's the case, when you look over here, everything's going to cancel out. It doesn't matter that this one and this one add together because this cancels this and this cancels this. Now, if it doesn't work, when you look at light from 4 different places, all you have to do is keep dividing in half, and eventually you would get to a point where overall you would have destructive interference. So the argument that they gave you here for destructive interference, you can just keep doing that, and if you keep dividing things in half, eventually you're going to find that you have pairs of waves which all cancel out. So we want to consider the path length difference in our example here. If you compare the difference between the path length here and the path length here, and it is equal to an odd number of wavelengths, so that would be m times a wavelength, then when you compare the path length difference between this point and that point, that would be equal to m divided by 2 times a wavelength. And if m is odd, then you have some integer plus a half number of wavelengths, which is destructive interference. If you have an even number of wavelengths, then that's where you just have to keep going, because eventually, if you keep breaking it down into more and more points, eventually you're going to come to the point where you will get a half of a wavelength as the path length difference. So any even number that you have, so let's say the path length difference between this point here and this point here is 8. You divide that by 2, you get 4. You divide that by 2, you get 2. You divide that by 2, you get 1. You divide 1 by 2, and you get a half. So you just have to keep breaking it up into more and more pieces, and eventually you're going to find that you have destructive interference overall because you have a pair of waves canceling out. And if every point that you have, if there's another point which cancels it out, then overall it's going to be destructive. Okay, so that's page 10. Then on page 11, you're going to do a graph of y versus m for the data that you have on page 15. So if you have the green laser, do that here. This is m. Y is half of what you measured. And for that, we're using this formula here. A was printed on the diffraction wheel. You should have that recorded. It probably tells you somewhere in the lab manual which value of A you are supposed to use. The distance D you should have recorded. That's the distance from the slits to the wall. And if you graph y versus m, then the slope is equal to d times lambda divided by a when you do a linear fit. So the slope is equal to d times lambda, divided by a. Solve for lambda. The uncertainty in the slope is equal to d divided by a times the uncertainty for lambda. Solve for the uncertainty for lambda and give me lambda plus or minus the uncertainty for lambda. If you are doing this for the green laser and you did the other graph for the green laser, it's the same wavelength for both, so those values should be close to each other. And then on the next page, if you had time to do it with the red laser, then you're going to do the same thing here for the double slit and the single slit, so that you will have two values for the green laser, one from the double slit, one from the single slit. If you did the red laser, you can put those in too. Write down the recorded value of the wavelength for the green laser and the recorded value. This was printed on the back of the laser. And then you can answer the questions on page 13, and that concludes the single and double slit lab.